Welcome students. So in this lecture we will cover three main topics. We will see the definition of mass moment of inertia. Then we will cover two topics. The second topic will be on mass moment of inertia of circular disk, and third topic will be mass moment of inertia of a thin rectangular plate. So let us start today's lecture. We will start with the definition of mass moment of inertia, and we are quite familiar with this definition because at the start of this topic we learned about moment of inertia. So let us read the definition again. It is a measure of the inertia of the system, that is a measure of the resistance the system offers when we try to set it in rotational motion. So we know that if we have to rotate this wheel about this particular axis which is perpendicular to this wheel, then wheel will offer some resistance against its rotation. So that resistance or that measurement of resistance will be called as mass moment of inertia of this wheel. Let us understand this through an example. Consider a body of mass m which is to be rotated about an axis, let us say AE dash. So over here one body is shown, and let us say we want to rotate this body about this axis AE dash. So we will call this as axis of rotation, and its direction also shown. Let us say it consists of n number of elements of mass delta m1, delta m2 up to delta mn. And let us say r1, r2 up to rn are the distances of these masses from the axis of rotation. So we have divided this body into n number of elements, and we considered their masses as delta m1 up to delta mn. And their distances from the axis of rotation is marked as r1, r2 up to rn. Then the moment of inertia will be given by this formula. So that will be equal to r1 square delta m1 plus r2 square delta m2 up to nth particle. So this equation will gives us that what resistance body will offer against its rotation about the axis, given over here as a dash. And we can write this equation in terms of integration like this, that I is equal to integration of r square into dm, where m is the mass of the smallest element considered by us in the body, and r is its distance from the axis of rotation. So when we'll multiply the mass of that element with the square of its distance from the axis of rotation, and when we'll do this for all the elements of the body and we'll add those terms, then we will get mass moment of inertia of the whole body about that axis, and its unit is given as kilogram meter square. Now we will discuss how we can derive equation for mass moment of inertia of circular disk. So let us assume that this is a disk, and this is the centroid of disk, and let us say the radius of disk is r units, and we want to find moment of inertia, that is mass moment of inertia of this circular disk about, let us say, z axis, which is normal to its plane. So we want to find iz. So over here its top view is shown. This is a circular disk, this is a centroid, and its radius is r. So let us see how we can derive the equation for mass moment of inertia of this circular disk about an axis which is a centroidal axis because it is passing through its centroid and it is normal to its surface. Okay, so this is the disk, and let us say mass of the disk is m and radius of the disk is, let us say, r units. Now, in order to find mass moment of inertia of this circular disk, we have to assume an imaginary ring in that disk. So let us say the distance of that ring from the center, or we can say the radius, is x, and its thickness is, let us say, dx. So if we have to find area of this imaginary ring, then we can say it is equal to 2 pi x into dx. So that will be the area of imaginary ring, 2 pi x into dx. Okay, now we will find mass of this imaginary ring. So how we can find the mass of this imaginary ring? We know that density is equal to mass per unit area. Fine. So that formula we will use over here. We want to find mass of this imaginary ring. So that will be equal to the product of its density into its area. So we will say mass of imaginary ring is equal to rho, which is its density, into its area. So that will be mass of this imaginary ring. Now what next? Next we will find moment of inertia of this imaginary ring about the centroidal axis O, about which we want to find mass moment of inertia of the whole disk. So let us say that is given by di. So what will be the value of di? We know that mass moment of inertia of any body is equal to the product of its mass and the square of its distance from the axis about which we want to find its mass moment of inertia. So it means di will be equal to rho 2 pi x dx. So this is what? This is the mass of imaginary ring multiplied by its distance from the axis. So that is x. So we have to take the square of that distance. So if we will solve this further, we will get rho 2 pi x cube dx. So we got the value of mass moment of inertia of this imaginary ring about the centroidal axis. So once you know that value, then you can find mass moment of inertia of the whole circular disk about the same axis by integrating that value between limits 0 to r, that is the radius of circular disk. So we will call that as moment of inertia of circular disk I will be equal to integration of di between 0 and r. So let us do this in order to find the value of I. So we know di is equal to rho 2 pi x cube dx. So we have entered that value over here. Now after that what we will do? We will keep rho and 2 pi outside the integration because these are constant. And we will take limits of integration from 0 to r. So when we will integrate it, we will get its value as x4 by 4, and we know that we have to apply limits to 0 to r. So let us apply the limits. So we'll get final result over here as rho 2 pi r4 by 4. And this will further reduce to rho pi r4 by 2. After that, what we will do, we can write this further as rho pi r square. We can take r square outside into r square by 2. Now observe this term carefully. What is pi r square? Pi r square is the area of this circular disk. And if we will multiply area by its density, that will be called as mass of that circular disk. It means we can replace this term by m, that is the mass of the circular disk. So final answer of moment of inertia of this circular disk about its centroidal axis, which is perpendicular to its plane, will be given by mr square by 2. Now in the next part of this lecture, we will learn about mass moment of inertia of rectangular plate. So let us see how we can derive its formula. Suppose we have this rectangular plate and its length is b, and let us say its height is d, and let us say its thickness is t units. And this is the centroid of this rectangular plate. We know it lies at b by 2 and d by 2. And in this lecture we will find mass moment of inertia of this rectangular plate about the centroidal axis, which is a horizontal axis labeled over here as x-axis, and it is in the plane of rectangular plate. So let us see how we can find the value of Ix. So what is the first step? First step is, like the previous example, over here we have to consider one elementary strip. So we have considered one elementary strip which is at a distance of y units from the main axis, and let us say the thickness of that elementary strip is dy. Now after that we will say mass of the rectangular plate m. It is given by density into volume, that we know. So rho is taken as density into what is the volume of this plate. It will be equal to length into width into thickness. So it will be b dt. So that is why we have written over here rho dot b dot t dot t. So this is the mass of this rectangular plate. So first step is find the mass of the rectangular plate. After that we will talk about the mass of the elementary strip. So let us label that as dm. So it will be equal to density into volume, of course. So density is rho. What will be the volume of that elementary strip? It will be equal to b length into dy into t. That is the thickness. So over here we have written rho dot b dot t into dy. So this is the mass of the elementary strip dm. So once you get this mass, then you can find moment of inertia of this elementary strip about the main axis by multiplying that mass with the square of its distance from the main axis. And let us denote that as di, and it will be equal to dm dot y square. Now once you get the mass moment of inertia of the elementary strip about the main axis, now it will be easy for us to get the mass moment of inertia of the whole plate about the main axis, that we can get by integrating di between limits minus d by 2 and d by 2, because this axis lies exactly in the mid of this total distance. So we have to cover this distance on both sides of the axis. So this will be minus d by 2, this will be d by 2. So let me write this value again. So Ix, that is mass moment of inertia of the whole plate about x-axis, is equal to integration of the mass moment of inertia of the elementary strip about the main axis between the limits minus d by 2 to d by 2. And what is di? That we already know, it is equal to dm dot y square. And what is dm? Dm is rho bt dy. So put these values in this equation. So we'll get di as dm dot y square. So replace dm by rho bt dy, which we calculated in the previous step. Now after that we will take rho bt common because these are constant, and we will integrate y square dy between limits minus b d by 2 to d by 2. So let us integrate this between limits minus d by 2 to d by 2. So when we will do this integration, we will get y cube by 3, and limits are minus d by 2, d by 2. So now put these limits also. So we'll get d cube by 24 plus d cube by 24. So we'll get 2d cube by 24. So that will be equal to d cube by 12. It means we'll get rho bt d cube divided by 12. Now let us see carefully over here. If I take d outside, means if I write rho bt d into d square by 12. So rho bt d will be mass of the plate, because BTD is the volume of the plate. BDT, the product of these three will give you volume. Volume multiplied by its density will give you mass. So we can replace rho BTD by M. So final equation will become MD square by 12, where D is the height of the rectangle, or we can say that side of the rectangle which is perpendicular to the axis about which we want to find the mass moment of inertia of the rectangular plate. So I hope these two derivations are clear to you. Thank you very much.